Good evening all. Our next topic in the third module is the photovoltaic cell or PV cell. The PV cell is composed of semiconductor material which combines some properties of metals and some properties of insulators. So the properties of a semiconductor lies between that of metals and insulators. It makes it uniquely capable of converting light into electricity. When light is absorbed by a semiconductor, photons of light can transfer their energy to electrons, allowing the electrons to flow through the material as electrical current. This current flows out of the semiconductor to metal contacts and can drive electric loads. Solar cells are semiconductor devices that produces electricity from sunlight through photovoltaic effect. Sunlight strikes the cell. When sunlight strikes the cell, photons with energy above the semiconductor band gap impart enough energy to create electron-hole pairs. And these electron-hole pairs are responsible for conduction. A junction between dissimilarly doped semiconductor layers sets up a potential barrier in the cell which separates the light-generated charge carriers. So we can have P and N type material. They are dissimilarly doped. When a PN junction is formed, a potential barrier is created, and that separates the light-generated electron-hole pair from the junction. So the electrons are forced to flow through the external circuit. So this barrier or separation induces a fixed electric current and voltage in the device. The electricity is collected and transported by metallic contacts on the top and bottom surfaces of the cell. The metallic contacts are placed on the P side as well as N side. Here you can see a PV cell, phosphorus doped N-type material, which is a thin layer around 0.3 micrometer thickness on the top, and a boron doped, that is P-type material P-type silicon material on the bottom. It will be having around 250 micrometer thickness. So the N-type layer is thinner compared to the P-type layer. When a PN junction is formed between these two, a potential barrier will be created at the junction. So when solar radiations are subjected on this device, it creates electron-hole pairs. Electrons as well as holes are repelled from the PN junction. So the electrons are forced to flow through the external circuit, creating a current flow. So a load is connected, a lamp load is connected across this device, and due to the current flow, it glows. A typical silicon PV cell is composed of a thin wafer consisting of an ultra-thin layer of phosphorus doped, that is N-type silicon, on the top of a thicker layer of boron doped P-type silicon. An electrical field is created near the top surface of the cell where these two metals are in contact, called PN junction. When sunlight strikes the surface of a PV cell, this electrical field provides momentum and direction to the light-stimulated electrons, resulting in a flow of current when the solar cell is connected to an electric load. This is the structure of a solar cell. N-type material, 0.2 micrometer thickness, is placed on the top, and P-type P layer is provided on the bottom, 250 micrometer thickness. So this PN junction is being created here. Then a metal electrode is provided for electrical connection at the bottom from the P side, as well as on the N side also metal electrode finger is used for connection, taking the connection. Junction is shown between P and N type material. This is the construction. So the cell is acting as a battery. It is a PN junction, looks like a diode, but the operation is in the reverse manner. So current flows through the external circuit when the photovoltaic cell is subjected by solar radiations. So the PN junction can be represented as a battery which drives current in the external circuit. Principle of working. Two important steps involved in the principle of working are: one, creation of positive and negative charges, that is electrons and hole in the solar cell by solar radiation. So when solar radiation is subjected on the PN junction, electron-hole pair is being created by absorbing the energy of photons. Then two, separation of positive and negative charges by the potential barrier or gradient within the cell, so that the electrons are forced to pass through the load circuit. The energy E of a photon is related to wavelength lambda by the equation E is equal to hc by lambda, where h is the Planck's constant given by 6.62 into 10 raised to minus 27, and c is the velocity of light. We know that it is equal to 3 into 10 raised to 8 meter per second. Substituting the values of h and c, we get the energy as 1.24 divided by lambda. Lambda is the wavelength. Then photovoltaic conversion, we have seen the solar cell already, PN junction. When solar energy is being subjected on this cell, electron-hole pair, you can see positively charged holes and negatively charged electrons. Due to the presence of potential barrier, the electrons are forced to move away from the barrier as well as holes also. So the electrons are moving to the negative terminal of the battery and forced to be driven through the load circuit and reach the positive terminal and combine with the holes. Materials suitable for absorbing energy of sunlight are semiconductors like silicon, cadmium, telluride, gallium arsenide, etc. In a semiconductor, the electrons occupy one or two energy bands, that is the valence band and conduction band. In the valence band, electrons are at lower energy level compared to conduction band. This difference in energy level is called band gap energy, represented as Eg. Photons of sunlight having energy E greater than band gap energy Eg are absorbed in the cell material and excite some electrons to the conduction band. These electrons jump across the band gap to conduction band, leaving behind holes in the valence band. Thus, electron-hole pair is being created. The electrons are made to flow through an external circuit, causing a DC current flow. The current voltage characteristics. The performance of a solar cell is displayed by plotting its BI characteristics. It is seen that current first stays constant as the voltage increases. It then rapidly falls to zero when voltage is the open circuit voltage VOC. The power delivered by the cell is also plotted as a function of voltage. You can see the diagram. Current is plotted along the x-axis and voltage along the y-axis. Power is also drawn here along with current against voltage. You can see the current initially the value is ISC when voltage is 0, then stays constant, then rapidly falls to 0 when the voltage becomes equal to open circuit voltage. Then power rises with voltage and reaches maximum when voltage is Vm and current is Im, and it falls to 0 when the voltage is open circuit voltage. When the when there are different intensity of solar radiations, the characteristics can be, the voltage current characteristics can be shown in this way. High insulation will be having more current. For the same voltage, we will be having more current. For low insulation, current is becoming lesser. We know that power is equal to voltage into current. So for higher insulation, the power generated will be more, and for low insulation, power generated will be lesser. Then the normal operating point, that is the maximum power point, is shown in the graph. Corresponding to this voltage, the operation of the solar cell is being adjusted. The power increases linearly from 0, reaches maximum, and then decreases to 0 when voltage corresponds to VOC. The maximum value of voltage is Vm when the power is maximum. The ratio Im/Vm divided by Isc/Vsc is called the fill factor of the cell, and its value lies between 0 and 1. Equivalent circuit of a solar cell. This is the equivalent circuit of a solar cell. It is represented as a current source of Isc. Then the reverse junction current is shown by Ij flowing through the solar cell. Then shunt current Ish flowing through the shunt resistance, and series resistance is shown connected in series with the cell. And load current is represented as I, load is represented as RL, voltage across the load is represented by V. The circuit consists of a current source supplying Isc. Rsh and Rs are the internal shunt and series resistances. If If is the current at the PN junction called junction current. Ish is the current through shunt resistance. I is the current flowing through the load resistance RL and having a voltage drop V across it. Usually the RSH is much greater than the load resistance, so that most of the current flows through the load and maximum power will be transferred to the load. The internal series resistance is much smaller, that the power dissipated in it is negligible. The simplified equivalent circuit is shown here by avoiding RSH, RS, etc. The same equivalent circuit is redrawn by avoiding RS and RSH. The load current I at fixed temperature and solar radiation can be related to voltage as follows. I equal to Isc minus I0 into exponent of exponent of EV by KT minus 1. I0 is the reverse saturation current or dark current. E is the charge of one electron given by 1.602 into 10 raised to minus 19. K is the Boltzmann's constant, 1.381 into 10 raised to minus 23. T is the absolute temperature in Kelvin, and Isc is the short circuit current. The power from the cell is given by power is equal to voltage into current. We have voltage as V and current is given by this expression. Isc minus I0 into exponent of EV by KT minus 1. So that's all regarding the equivalent circuit, power expression, current expression, characteristics of solar cell. So we shall stop here. Thank you for listening.